To build and consolidate new synapses, neurons must continuously reshape their outer membranes. This plasticity requires a steady supply of cholesterol to form ordered membrane domains. Because neurons cannot synthesize enough cholesterol on their own, they are entirely dependent on external deliveries from nearby astrocytes. The accepted model treats this delivery as a straightforward two-body problem. Astrocytes produce the cholesterol, package it into 20-nanometer apolipoprotein, or ApoE, particles, and release them. The neuron then receives those particles through its surface receptors. This uptake requires an intermediary. The neuron uses cell surface heparan sulfate proteoglycans as essential co-receptors. These sugars grab the passing ApoE particles and hand off to endocytic receptors like LRP1 for internal processing. The prevailing logic follows a direct line. If heparan sulfate is the designated capture mechanism, an ApoE variant with a higher binding affinity for that sugar should secure more cholesterol, support better plasticity, and lower a patient's risk of Alzheimer's disease. This chart plots the 4 documented ApoE isoforms, measuring their in vitro binding affinity to heparan sulfate against their clinical risk of driving Alzheimer's disease. The data completely inverts the prevailing logic. The E4 isoform binds with the highest affinity of any variant, yet carrying the E4 allele constitutes the greatest genetic risk factor for the disease. On the opposite end is the Christchurch variant. It binds at only 40% the affinity of the neutral E3 baseline. Yet a woman carrying this variant homozygously demonstrated nearly 3 decades of clinical resilience against an autosomal dominant early-onset Alzheimer's mutation. A framework built solely around broken neuronal receptors cannot account for this data. If tighter binding correlates to the disease and weaker binding confers resilience, the field is operating with an incomplete equation. The missing variable is the journey itself. The supply chain has 3 steps: release, transit, and capture, but the accepted model ignores the space between the cells. The cargo, the ApoE lipoprotein particle, measures roughly 20 nanometers in diameter. The extracellular space it must traverse in a living brain is on the order of 40 nanometers wide. Forcing a 20 nanometer object through a 40 nanometer channel creates severe physical hindrance. This tight space is not an empty aqueous void. It is a dense, highly charged lattice comprised of hyaluronan chains and lecticans. The ApoE transit is a complex physical navigation problem. The particle's mobility is restricted both by the tight geometrical ratio of the channel and the electrostatic friction of a highly negatively charged gel. Heparan sulfate is not exclusive to the neuron surface. It exists in 2 completely separate locations, both of which compete simultaneously for the exact same binding interface on the ApoE particle. The first location is the productive bed at the neuronal surface. Here, heparan sulfate is backed by endocytic receptors, meaning binding terminates in cellular uptake. The second location is the unproductive bed, distributed throughout the interstitial matrix. It contains heparan sulfate, but lacks receptors. When an ApoE particle partitions into the productive bed, it docks seamlessly, delivering cholesterol to the membrane. But when it partitions into the unproductive interstitial bed, it binds to a dead end, detained entirely in the tissue. This competition explains the affinity paradox. Because the E4 variant possesses the highest binding affinity, it is rapidly captured and detained by the unproductive matrix bed long before it can reach the neuron. Conversely, the Christchurch variant's exceptionally low affinity allows it to slip past the matrix traps. It avoids detention, remaining mobile enough to complete the journey. Molecular affinity does not dictate health or disease in a vacuum. The clinical outcome is governed entirely by the volumetric ratio of the productive capture bed against the unproductive trap. If this delivery system functions properly in young brains, a specific physical mechanism must trigger the shift that causes it to fail as we age. Analysis of human Alzheimer's hippocampi provides the data. In diseased tissue, the total sulfated glycosaminoglycan content and the specific levels of heparan sulfate rise drastically. The trap physically expands. The driver of this chronic expansion is sustained noradrenergic drive. Decades of chronic stress and prolonged arousal place continuous pressure on the brain's regulatory systems. This chronic noradrenaline signaling actively upregulates a specific extracellular enzyme known as matrix metalloproteinase 9, or MMM9. Elevated MMP9 actively cleaves syndecan ectodomains, shearing the primary heparan sulfate capture receptors from the membrane. These severed structures don't disappear, they drift into the interstitial space, subtracting volume from the productive bed and adding it to the unproductive bed. The disease state is a simultaneous double blow. The neuron sheds its ability to catch incoming shipments, while the surrounding matrix trap grows thicker and more dense. This systems at once, converging at a single zero-sum docking station on the neuronal surface, the apoE2 receptor. apoE2 requires a specific N-sulfated heparin sulfate clasp to successfully bind reelin. Reelin is a critical signaling molecule that suppresses the toxic hyperphosphorylation of tau inside the cell. As MMP9 shreds the extracellular bed, this receptor loses its structural support. Without the necessary sugar clasp, reelin cannot bind. The consequence is systemic failure. Stripped of the heparin sulfate bed, the neuron is starved of the cholesterol required for plasticity and simultaneously loses the reelin brake, allowing tau to hyperphosphorylate and destroy the internal cytoskeleton. Meanwhile, the apoE particles permanently detained in the overgrown matrix trap face their own grim end. Over time, these stalled carriers degrade, rupture, and dump their aggregation-prone amyloid payloads directly into the surrounding tissue. This physical debris matches the definitive pathology observed in human patients. The plaques are the terminal residue of millions of detained extracellular carriers that never reached their destination. We are looking at a neuron locked in a chronic, failing attempt to rebuild its synapses, surrounded by the rotting debris of supply shipments that were intercepted just outside its doors. This model requires us to confront the seminal literature in the field. Previous studies successfully proved that neurons associated with the E4 variant exhibit reduced uptake of cholesterol. But those foundational studies share a structural flaw. They were conducted using in vitro assays, measuring a neuron in a sterile dish, devoid of an extracellular matrix. In living tissue, delivery failure happens before the particle reaches the receptor. It gets entangled in the space between cells. Measuring cellular uptake in a vacuum proves that the neuron receives less cholesterol, but it completely masks where the loss actually occurs. Experimental design must adapt. Researchers must measure the physical mobility of lipoprotein particles within aged tissue itself, rather than in an empty liquid medium. We cannot cure a disease of the supply chain by examining the final destination. To understand the failure, we must investigate the crowded cleft.